All right, let's jump straight into this explainer. We are looking at Chapter 21 of Observability Engineering, zeroing in entirely on observability for large language models. Because, look, here's the reality a lot of developers are facing right now. Building an AI demo, it's incredibly easy. You grab an API key, and boom, you've built something that looks like absolute magic in an afternoon. But pushing that application to production, yeah, that is a completely different beast. This quote from the source really hits the nail on the head and sets up our core conflict perfectly. Users and engineers are wired to expect software to be deterministic, right? You put a specific input in, you get a known, predictable output out. But LLMs? They are inherently non-deterministic. They are wildly unpredictable. You could literally feed them the exact same input 10 times and get 10 completely different responses. So, to navigate this, here is our roadmap for today. First, we'll hit the AI production reality. 2, why traditional observability fails. 3, Evals, testing the unpredictable. 4, designing telemetry for LLMs. 5, harnessing and analyzing data. And finally, 6, the continuous improvement flywheel. Let's get into it. Okay, moving to Section 1, the AI production reality and what it actually takes to move past the demo phase at scale.
We really have to continually contrast traditional software with AI engineering. Traditional systems, they do exactly what they are coded to do, operating on highly predictable inputs with rigid logic. LLMs, on the other hand, operate in this impossibly vast, unpredictable space of human language. They're generating responses based on probabilities, not processing rigid code. And let's be honest, your users are inevitably going to find the most creative, bizarre ways imaginable to ask for the exact same thing, or even try to trick the model entirely.
Which brings us to Section 2, why traditional observability fails, and why our usual monitoring tools just aren't enough anymore.
This shift fundamentally rewrites our definition of a successful user interaction. In traditional systems, we lean heavily on proxies for user experience, things like latency or error rates. Fast usually means good. But with LLMs, those traditional proxies completely fail us. Why? Because a lightning-fast hallucination from an AI is actually so much worse than a slower, accurate response. Even if you measure something like time to first token, it simply doesn't matter how incredibly fast that first token shows up if the overall answer is completely fabricated. So how do you even test something that unpredictable? Let's look at Section 3, Evals, testing the unpredictable. The big takeaway here is that evaluations, or just evals for short, are absolutely foundational. You can think of them as your new unit tests, but there is a catch. Unlike traditional unit tests that strictly pass or fail, evals are uniquely designed to handle the fuzzy, probabilistic nature of AI logic. They can return a pass, a fail, or a maybe. They give you a vital yardstick to measure performance against, letting you finally quantify the unquantifiable.
And we basically break these down into two distinct types. On the left side, you've got format evals. These are pretty straightforward. They use a simple scoring function like a string matching heuristic where you know the exact expected value from your golden data and you just check if the model spit it out. But on the right, task evals. These are super fascinating. They are fuzzy, highly subjective tasks based on actual production monitoring, where there isn't one single right answer. Instead, you're essentially using an LLM as a judge to score the actual steps the model took during a complex workflow, like a root cause analysis.
But actually, here is the real catch. You can't evaluate what you can't see, leading us right into Section 4, designing telemetry specifically for LLM applications.
Let's look at the core things you need to track. You absolutely must track token counts, the raw inputs and outputs sent to the model, and crucial user feedback signals, even just a simple thumbs up or down. That feedback is gold since latency isn't a reliable proxy anymore. Also, a huge piece to highlight here is cost tracking. GPU time is wildly expensive, right? Deriving your costs at query time based on token usage is a fantastic trick. It lets you easily compare the price of different prompt versions without completely cluttering up your baseline metrics. And the really good news? You don't have to invent a way to track all this from scratch. By utilizing OpenTelemetry or OTel generative AI conventions, you get a highly standardized way to capture all these essential fields. Sticking to these conventions ensures you're grabbing usage tokens, model names, sampling params, and system prompts in a way that keeps your telemetry data perfectly portable across your entire ecosystem. Okay, Section 5, harnessing and analyzing data. Let's look at what actually happens when all this telemetry meets messy production data. I want you to consider a real-world mystery from the source text involving a product called Honeycomb Canvas, which is an AI chat experience. The AI agent was tasked with finding the root cause of a performance regression. But instead of doing that, it completely derailed. It went on this bizarre wild goose chase and ignored the actual issues. So what happened? Well, the telemetry revealed the culprit. The model stumbled across a data column named is_slow. Now, to us humans, is_slow obviously just means a request took longer than usual, over 500 milliseconds in this case. But the AI, it can't read our minds. Lacking that human context, it imputed its own completely wrong meaning. It assumed is_slow was an external event, like a load test or a feature flag, and it blamed a latency entirely on that field, completely ignoring the real underlying factors.
So how do you fix a hallucination like that? The solution was actually incredibly simple. The engineers didn't use some magical, ultra-complex prompt engineering. They just updated the deterministic software harness, the normal code wrapped around the AI, to include a simple text description of what that field actually meant. The moment the AI had that context, it instantly course-corrected. It's proof that good old-fashioned code is often the best way to fix an AI hallucination.
Here is another great example of telemetry saving the day. When the Honeycomb Query Assistant first launched, it was hitting a massive 25% error rate. Literally 1 in 4 requests just failed. Without observability, you'd probably just assume the LLM was garbage. But the telemetry told a much more specific, actionable story. The AI just kept returning invalid, truncated JSON structures. Because the engineers could see those exact truncated outputs in their logs, they knew exactly where the validation was failing. So they stepped in and patched the software harness plumbing to handle those parsing errors gracefully. They didn't just cross their fingers and endlessly tweak the LLM's system instructions. That deterministic code acts as an absolutely essential bridge between the unpredictable AI and your app. Which brings us to our climax. Section 6, the continuous improvement flywheel, and how we synthesize all of this into a repeatable routine. This right here is your mental model for success. It is a continuous loop. First, you gather production telemetry from real user interactions. Second, you take the edge cases and failures you found in that data and use them to update your evaluations. Third, those new evals dictate exactly what updates you need to make to your deterministic code harness. And then, the cycle repeats. Telemetry feeds evals, evals inform improvements, and those improvements show up as better telemetry. But wait, there is a very critical warning here. While automating this loop with an LLM as a judge is amazing, you absolutely cannot skip manual review. You have to regularly hand-check a sample of your task evals. Human eyes are mandatory to catch subtle context errors, like that is slow hallucination we talked about, because an automated AI judge is going to routinely miss those. Another huge point. Ignore the public benchmarks. Frontier AI labs love boasting about high scores on generic benchmarks for truthfulness or tone, but those graphs are super misleading. Think about it. If your app scores perfectly on a public benchmark, but your production telemetry shows it is completely failing your specific users, well, that benchmark is utterly useless. Your own production telemetry is the only ground truth that actually matters. The ultimate takeaway is this. Taming the non-deterministic beast of AI is not about luck, and it's definitely not about crafting one magical prompt. Taking a 25% error rate down to 1% is achieved through the boring, methodical, highly effective practice of rigorous observability. It's about applying the exact same engineering rigor to AI that we've always applied to traditional software. So I'll leave you with this final question. When you push your next AI feature, are you going to let it run blind in production, crossing your fingers and relying on generic benchmarks and good vibes? Or are you ready to use the telemetry and evaluation flywheel we've explored today to finally turn the unpredictable unknown into actionable intelligence? The choice is entirely yours. Thanks for joining me on this explainer.